All right, good afternoon, and welcome to this video where we are going to go through chapter 15 on nuclear chemistry. This is the last chapter in our unit. This is the last chapter in the course for Chem 100 in this semester. So, what are we really getting into here with nuclear chemistry? Well, first thing we need to talk about with regard to nuclear chemistry is radioactivity. Now, radioactivity is the spontaneous emission of particles from a source. And with that spontaneous emission of particles come energy that we know as radiation. Now, in total, there are two types of radiation. There's electromagnetic radiation. This would include all forms of light and other kinds of energy, cosmic energy, gamma rays, X-rays, infrared, microwaves, other kinds of things as well. The other part of radiation comes from the particulate. That is, there is a mass, a particle that is given off when unstable atoms disintegrate, break apart. And that disintegration comes with a particle, and that particle has a certain amount of energy associated with it, and it usually comes with a release of electromagnetic energy as well. Now, there's one other term that we need to discuss in here, and it's the idea of an ionizing radiation. Ionizing radiation takes place when we have radiation of either type that when it encounters other material will cause that other material to ionize. That is, form charged particles. Usually this comes in the form of losses of electrons. So we encounter the ionizing radiation. The ionizing radiation strips electrons from our cells, and our cells react to that loss of electrons, usually in a negative way. Now, radioactive decay overall is the spontaneous emission of this type of radiation, either the electromagnetic or the particulate, or in some cases both. The things that do the radioactive decay are radioactive atoms. These are unstable atoms that will give off this excess energy, this excess matter, or both in the form of ionizing radiation. So what we have in a radioactive decay is an unstable nucleus that will break apart. And the process of breaking apart is called radioactive decay. And what will form is a more stable nucleus, a particle, and energy. This is what occurs in radioactive decay. We have an unstable nucleus. That unstable nucleus is so full of excess energy that its motion literally breaks apart the nucleus. We get a more stable nucleus as a result. We also get the particle that was lost and the energy that was lost that turned the unstable nucleus into a more stable one. Now, there are some terms that come along with this. One of those terms is a nucleon. A nucleon is basically just a term that we use to describe nuclear particles. In particular, protons, neutrons, and small combinations of them to make small atoms. Just some reminders. We talked about this. This goes back to, I think, chapter 2. When we talked about isotopic or other kinds of notation. The term Z represents the atomic number, that is the number of protons in a nucleus. N represents the neutron number, the number of neutrons in a nucleus. And the sum of those, N and Z, gives us A, the mass number. Now, where we have seen this before, if you can remember, we had this AZX notation, where we could describe an element. I'm giving the general element X here. We could describe an element based upon its atomic number, Z, and its mass number, A. And another way that we could describe it is simply by referring to the element by its mass number. So carbon-12, for example, is carbon with a mass number of 12. And so if we follow that all the way through, we see, okay, carbon is element number 6, 6 protons in that nucleus, 6 plus 6 neutrons would give us the mass number of 12. So these types of notations are very common in nuclear chemistry, and we'll take some time and kind of review them here in just a minute. And so where this comes about is, again, we saw those notations in the context of isotopes. We could look at the difference between an isotope of carbon-12 versus an isotope of carbon-13. And notice that really the only difference between them was the fact that we had the same number of protons, we had the same atomic number, but our mass numbers were different from each other. And so these two nuclei are different, even though they are the same element. Carbon-13 is more unstable, carbon-12 is more stable, and so carbon-13 is more prone to radioactivity as a result. Now we can kind of take that concept from chapter 2 and integrate it into this concept here in chapter 15 by understanding that another term for isotope is nuclide. And nuclides are simply isotopes that exist for a certain amount of time and have a certain energy to them. So when we refer to something as a nuclide, we can kind of think of them in the same way that we thought of isotopes. They're defined by an atomic number and a mass number. In other words, a symbol and a mass number. Nuclides exist all around us. In fact, there are over 3,000 nuclides that are known, but only about 250 of those 3,000 nuclides are actually stable. The ones that are stable exist on this so-called band of stability. The band of stability here are represented by these dots. And we can see that those that are not on the band of stability, so again, only about 250 actually are stable. Those that are not on the band of stability here do not exist from a stable standpoint and would be subject to radioactive decay, because if it doesn't exist on the band of stability, we know that it's going to have excess energy, and that excess energy is going to cause it to decay over time. These here are rarely prone to decay. In fact, they don't decay virtually at all. When the others do decay, they will emit radiation over the course of the process. And what we can see is that we can kind of break down the band of stability into two different zones. The first zone is right here. Atomic number 1 to 20. What we tend to see here is a 1-to-1 ratio of protons and neutrons. In this zone. And so this blue line here represents that 1-to-1 ratio, going all the way up to element number 92 here, which would be the atomic number of uranium. But here we can see 1-to-1 ratio of protons and neutrons. And so for our smaller atomic weight substances, that tends to be what we see. And that kind of shows itself in the periodic table too, right? If I look at the periodic table, I'll see that the average mass for carbon is 12. 12 would represent a 1-to-1 ratio of protons and neutrons, 6 and 6. For things like lithium with an atomic number of 3, its most competent molar mass is around 7. So really close to 1-to-1. We see with calcium, atomic number 20, average atomic mass just over 40. So in this early low atomic weight kind of group, we see that a 1-to-1 ratio is pretty common. But what we also see is that once we get off of that mark, not only does it go away from 1-to-1, it actually bends. This is not a straight line. This is a curved line. We can see that over time, this is going to curve up until we get to a spot right around here where we're talking about 1.5, really. 1.5 protons, or excuse me, 1.5 neutrons. Up here at the top. So from 1-to-1 to 1 to 1.5, we see that as our atomic masses, as our atomic numbers get bigger, we need more and more neutrons to kind of balance that out. Because you gotta think about it, what is a proton? A proton is a subatomic particle with a positive charge. And the more of those we pack into that tight space, the more repulsion forces we're going to start to see. And so the purpose of the neutrons in some way is to kind of act as a buffer and kind of separate those protons from each other so that they don't repel each other and completely fly apart. So we've covered the idea of stability. There are certain atomic isotopes that have stable isotopes. But what about the ones that aren't stable? What kinds of things happen to them? And so that's what this is going to get into here with radiation. In radiation, we're going to look at 3 different types of radioactive decay. And each of those is going to correspond to a different kind of result from a nucleus. So certain nuclei are going to be more prone to alpha particle decay. Other nuclei are going to be more prone to beta decay. Other nuclei are going to be more susceptible to gamma decays. It all depends upon the makeup of that nucleus itself. Now, how do those 3 types of properties differ from each other? Well, first of all, we have to understand alpha, beta, and gamma. There are actually 2 different types of beta decay. There's what is called electron or negatron emission. This is one that has a -1 charge. And then there's positron emission, where we have a positive charge. Notice that the only thing that really is different about each of them is the charge itself. They have no mass, or effectively no mass. They're about the size of an electron, but with one up with a +1 charge and one with a -1 charge. Alpha particles are, by contrast, larger. Their notation 4, 2, they actually have an atomic number. Their atomic number is 2. Their mass number is 4. So these are big, heavy, bulky decay particles. With that notation, another way that we can look at this is thinking of them as helium nuclei. So if I take a helium nucleus, 2 protons, 2 neutrons, 2 electrons, take away those 2 electrons, and just the 2 protons and the 2 neutrons, that would be an alpha particle. It is massive by comparison. Because again, we're talking about comparing a helium nucleus to an electron. The scale is very, very, very large. We're talking about a particle that's nearly 7,500 times larger, more massive than a beta particle. So when it encounters you, it's going to hit you with some significant impact. Now, this column here on the far right is kind of interesting. This is penetration power. So how good are these particles at actually penetrating material and causing ionization? When we see that alpha decay doesn't have a lot of penetrating power. In fact, most objects will block alpha particles pretty easily. And that includes things like paper, your clothing, 0.01 millimeters, 10 microns, not a very large penetrating power. They're easily blocked, they're easily stopped. With beta decays, we can see that negatron or electron emissions do have a good bit more penetration power, anywhere between 50 and 200 times the power. I'm sorry, 50 and 1,000 times the power of alpha particles. Positron emission doesn't tend to penetrate too much. Usually what we see is a positron will react with an electron and cause something called annihilation. They'll basically run into each other, react with each other. The positive and the negative will interact with each other and basically cancel each other out and produce a ton of energy when it does. Gamma decays, again, we have no mass, we have no charge, it's just pure energy. And we can see that the results, anywhere between 10 and 50, 10 and 100 times the penetrating power of a beta decay. So of these, we would look at gamma as being the most dangerous of the group. And then beta decays, and then alpha decays. So let's look at them a little bit more closely. Alpha particles. Again, alpha particles are the nuclei of helium atoms, in particular helium-4. They contain 2 protons and 2 neutrons, but because of their lack of penetrating power, because they are so easily blocked by relatively thin objects like paper, like your skin, they have very little harm to you unless they get into your body system somehow. Like you ingest them or inhale them or something, and they get through that barrier that way. Gamma rays, on the other hand, are extremely high energy electromagnetic radiation. They have no particle component to them whatsoever. And because it is pure energy with no particle to leave it behind, they are the highest energy. They have the most penetrating ability. That gamma ray is able to go straight through your skin, straight through your tissues, your bone, and into your organs. If you encounter gamma radiation, it is going to be very, very powerful and have an impact on your body. Beta particles, on the other hand, kind of fit in between the two. They are both particulate and energy, like we saw with alpha, but they are considerably smaller in mass, which means they are higher in energy than the alpha particles were. They are small, they are charged. They can be emitted from unstable atoms that are coming into speeds close to the speed of light, and they will penetrate that first layer of skin tissue and get into the subcutaneous layers underneath. As I mentioned before, there are 2 different types of beta particles. There's the positron. The positron has the same mass of an electron, but an opposite charge. And then there's the electron itself. So that's section 1 of our study of nuclear chemistry. We move on to section 2, and now we're starting to look at chemical reactions, or excuse me, not chemical reactions, but rather reactions of these nuclei, which we will call nuclear reactions. Now, when it comes to balancing nuclear reactions, we have to look at them slightly differently than what we would have before. So instead of worrying about, okay, I have this many atoms on this side and this many atoms on this side, and making sure that all my atom counts line up, what I have to look at instead are mass numbers and nuclear charges. That is what I'm going to ultimately try to balance here. And so if I look at my examples here, I can see that those are where I'm going to look at. So if I draw a line that cuts this reaction in half to my reactants and my products, the numbers on the top have to be even on both sides. So I have 232 as the mass of the thorium here. If I add together the 228 from the radium and the 4 from the alpha particle, I will get that same 232, which is what I was looking for. So from that perspective, I know that the mass has been evened out. It is equal now. On the bottom side, I would have to do a similar kind of look at the thorium's atomic number and comparing it to what is on the other side here. So thorium has an atomic number of 90. I can see that 88 of it is in the radium, and the other 2 is in the alpha particle. 88 plus 2 gives me the 90 that I was seeking on the other side. And so I can see that in either case, I'm going to have a matchup of masses and charges. Masses have to be equal, charges have to be equal. And if mass and charge are both equal, then I've got a balanced nuclear equation. So if I look at the thorium here, my thorium-231, I have 231 as the mass. 231 plus 0 gives me 231 for the mass on the product side. I have 90 as my charge. 91 plus -1 gives me 90 for the charge on the product side. This also applies to other kinds of reactions as well. This is an example of a fusion reaction here, where an alpha particle is slammed into a uranium nucleus to create plutonium. And if I look at it from that perspective, I'll see 238 plus 4 gives me a total of 242 as my total mass on the reactant side. 239 plus 3 1s. So this is 239 plus 1 plus 1 plus 1 gives me 242. So from a mass perspective, I'm even. From a charge perspective, 92 plus 2 is equal to 94 on the reactant side. 94 plus 0 is equal to 94 on the product side. I've got an evenness on both sides as well. So this is an example of a more complicated nuclear reaction, but we apply the same kinds of principles to it as well. So let's look a little bit more closely. Alpha particles. When a nucleus emits an alpha particle, it's going to lose 2 protons and 2 neutrons. And so in total, its atomic number is going to decrease by a factor of 2, and its mass number is going to decrease by a number of 4. So when thorium undergoes an alpha decay, we take 4 off the top. 232 minus 4 is 228. We take 2 off the bottom. 90 minus 2 is 88 for that. And I would identify radium as element number 88 by consulting a periodic table. For beta particle emission, same kind of thing. My beta particle gives me a charge of a -1. So I'm going to actually add 1 to my atomic number. That's how I go from 90 to 91. So I went from thorium to protactinium. My mass number is not going to change at all, though, because the beta particle has no mass. So 231 before, 231 after. Again, the only change was in the mass number itself, or in the, excuse me, the atomic number itself. For positron emission, pretty much the same thing. Mass doesn't change, but the atomic number does. In this case, the atomic number is going to decrease by 1 to account for the charge of +1 on the beta particle. So I went from magnesium 12 to sodium here with 11. And then finally, gamma rays. Gamma rays come from a nuclear reaction where I have an energetic nucleus. You can see it's energetic because the protons and neutrons are all kind of out of whack here. They're all bunched up and, you know, kind of moving around a lot. And so as it undergoes that gamma radiation, notice that we go from very erratic to very stabilized, ordered kind of configuration. There is no mass change. There is no atomic number change. All that we are seeing is a metastable, that's what that M stands for, a metastable element or nucleus transitioning a metastable nucleus transitioning to a more stable nucleus. That's really all we are getting in gamma ray emission. So no changes in charge, no changes in mass, just a more disordered, more energetic state stabilizing itself and becoming more ordered and less junky. Let's do some examples of nuclear reactions and let's solve these problems. So what is component X in each of these? Now, the way to solve these is to keep in mind we need to conserve mass and charge. Now, from a mass standpoint, I see that up top here, I have 214 for the lead and 4 for the alpha particle. It gives me a total of 218. I would anticipate that since this is 218, this is the only component over here, its mass number would be 218 also. On the bottom side, I've got 82 plus 2 for the alpha particle is 84. So my mass number, or excuse me, my atomic number is 84 here. And so now I need to consult my periodic table. And my periodic table tells me that element number 84 is none other than polonium, PO. So X is polonium. So if I wanted to rewrite the whole thing, I could give 218 as my mass number, 84 as my atomic number, and this would be the element PO, polonium. In a similar fashion, I could do the same kind of thing with number 2, thorium 90, 234 is giving me a beta particle and an electron. And so I can kind of approach this and say, okay, 234 is what I'm trying to get to. 0 is what I have so far. So X must be 234 in this case. And on the bottom side, 90 is what I'm going for, because that is the atomic number of thorium. X, I don't know. -1 is the beta particle. And so to solve this, I would need to take 90 plus 1, which would be 91. So I've got a mass number of 234, an atomic number of 91. Once again, I consult my periodic table. My periodic table tells me that element number 91 is Pa, protactinium. And so I could rewrite this again. 234, 91, protactinium, Pa, is my mystery particle. Number 3, very similar to number 1. I can add together my numbers. 11 plus 0 gives me an 11. 5 plus 1 gives me a 6. Element number 6 is carbon. And so I'm looking at 11, 6, carbon as the particle that decays to give us the boron 11 and the positron, the beta plus particle. So that's all that there is to these particular problems, is to find the missing piece, whatever it is, whether it's an atom, a nuclide like these, or the particle itself, is to just simply add and subtract to figure out what is missing, so long as I conserve mass and charge. And so I'm going to stop the video right here. In our second video, we will discuss half-life and some particular applications of radioactivity to things that we encounter in our daily lives. But until then, take care. Have a good afternoon.